So, okay, remember when I said, oh, I said we were going to do a quiz today. I don't have a quiz for you. Okay. So we'll have to do a quiz next week, I guess, if I remember. That just popped into my head. Okay. So remember that there was a very brief intermediate step between talking about particles and talking about rigid bodies. And that was particles where we don't know the connections between them. What can we say about collections of particles? So, so um, what can we say about collections of particles that are not organized into a rigid body? Um, well, we can't use the moment equation the way that we're used to using it because we don't know, because the moment of inertia of the thing is going to change, as the different particles move around. So we can't do that, but there is one really useful thing that we can say about random collections of particles. Um, so kind of one useful thing. And that is Newton's law. Newton's second law says that if you add up all the force vectors applied to the objects by outside things, so I'm going to call that net external forces, that's equal to the mass of the whole system times the acceleration of the system's center of mass. Okay. So F net external, bless you, is the sum of the force vectors applied to the collection by things outside the collection. Okay. And then the mass is the total mass of the collection. And the acceleration of the center of mass is the acceleration vector of the collection's center of mass. Okay, so let's apply this to this problem. So we have 5 balls, each one has a mass of 0.2 kilograms. They're floating in space. An external load of 20 newtons is applied to one of the balls. And that 20 newtons is pointing to the right. So for this example, F net external is equal to 20, 0. Okay. The mass, the total mass of the collection is 5 times 0.2, so that's 1 kilogram. And so Newton's second law says 20, 0 is equal to 1.0 times the acceleration of the center of mass. And so the acceleration of the center of mass is 20 meters per second squared. Yeah.
And it makes sense because just one thing for that, the ball itself would be going 5 times as fast, but when you consider all five together,
Yeah. And
they're together going.
that's right. So let's think about a few different possible scenarios, you know. So the first one is, okay, what if say all of these balls are in contact and you apply this force to one of them? Okay. Um, well, then that force is going to affect the acceleration of all of these things. But the internal forces between the different bodies are going to keep the one that you're hitting from accelerating as much as if it were by itself, you know? And so these would all go, I don't know, what this is like a pool break. So, I mean, they would go, uh, who knows? They'd all go different directions. But if you add up, and don't think of velocities, I think I might have just made that mistake, but these are accelerations, you know? So say these are the acceleration vectors. If you add up all those acceleration vectors, um, according to the rules of center of mass, or I guess if you calculate the center of mass, uh, you'd have to use the sum formula that says, you know, like acceleration is equal to 1 over the total mass times the sum of the individual mass times the acceleration of the center of mass of the acceleration of each one. So you'd have to use something like that to calculate it. But if you calculate the acceleration of the center of mass, um, it's going to be just the same as, you know, it's going to be 20, just the same as like in a second scenario where they're 50 miles apart from each other. And you just apply a 20 Newton force to this one. Well, then it makes perfect sense that the acceleration of the center of mass is going to be um, 20 meters per second squared, because this one's going to have an acceleration of 5 times that much, and then you're going to divide it by 5 to get the total. But even if they're in contact, you're going to get that same answer. Okay, so whether these particles have been set up for a pool break, or whether they're all separate from each other, or whether they're particles of pudding, you know, and you apply a 20 Newton force to a corner of this pudding or whatever, the answer is the same. And that's a useful thing to keep in mind. Anybody have any questions about that? That
So anything you draw a circle around and apply a force.
Yes, anything you apply a circle around, um, that's right. And you apply, and then you know what the external forces are that are being applied to it. You know from Newton's second law what the acceleration of the center of mass of the stuff in the circle is. That's right. And it doesn't have anything, it doesn't have to be a rigid body. It doesn't have to be pool balls. It doesn't have to be pudding. It's, it can be any collection of particles. Like that's an incredibly strong thing to be able to say. But it just comes directly from applying Newton's second law to multiple things and then using the definition of center of mass. So what I'm getting at here is in either of these cases, in both cases, the acceleration of the center of mass is 20, 0. And that's surprising, but that's how it works. And so I think the example I gave before, like maybe it'll make a little more sense what I was talking about before. Imagine that you're, okay, forget about jumping. Imagine that you're like launched off the ground and, you know, some platform like launches you a foot or two off the ground. Okay. And say you want to get your center of mass as high as possible. Okay. So what can you do once you're launched to get your center of mass of your body as high as possible? You might think, I'm going to lift my arms up. I'm going to lift my legs up, do all this stuff. But if you think about it according to this rule, the truth is you can circle your body, and then all those internal forces, anything you decide to do, doesn't have any effect on what Newton's second law says. Once you're launched, you lift your arms up, lift your legs up, your center of mass, its motion is totally prescribed by the fact that the only external force on your body is gravity. It's surprising, but it's true. And so like when you watch like track in the Olympics and stuff, like you see people doing stuff in the air, like long jumpers. You see them, half of the long jumpers do this windmill thing, you know, and your first reaction is like somehow that must increase the, you know, how far their center of mass goes. But no, once you leave, I mean, if you leave out air resistance, which isn't a big thing in like a long jump. So once you leave the ground, you don't have any control of what your center of mass is going to do. No matter what you do, that's all internal stuff, you know. You don't have any control of what your center of mass can do. All that stuff they do with their arms and legs is just getting their body in a position to land so they don't fall back on their butt and lose distance or whatever. Okay, but their center of mass is going to do the same thing. Same with high jump, like it would be, so once you leave the ground in the high jump, your center of mass, its motion is prescribed. There's nothing you can do about it, you know? So why don't high jumpers just, this would be cool actually, like watch the Olympics and someone does their run up and jumps and then just stays totally straight. And they'd go over a height, you know, this high or whatever. They wouldn't be very good at high jumping. Their center of mass would still do the exact same thing. But the thing where like all the motions that you do in the air and stuff is just trying to maximize what your body gets over as your center of mass follows its parabola. And in fact, somebody who's very good at high jumping, like the Olympic people, when they're near like the top heights they can get, their center of mass never gets as high as the bar. It'll go close to a foot under the bar, and somehow still at each instant, the part of their body that's in line with the bar is over it. I mean, it's amazing, but that's how it works. Okay, so that was 5. 6, 7. Anybody have any questions about 6 or 7? 6, 7. I'm just trying to connect with the kids today. I know what you guys like. Okay, so either of these confusing to anyone? Okay. Okay, so we have, so I'm going to use my usual coordinate system that's like z coming out, x, y. And we're given the angle as a function of time. Gravity asks toward the bottom of the page. What's the external couple as a function of time? Okay, so we know that, okay, so if theta is equal to 0.05 t squared, then by definitions of angular velocity and angular acceleration, we know those as functions of time too. How do we get the angular velocity as a function of time? Yep. So remember, this is defined as the time derivative. This step only works in the plane. But if you're working in the plane, you can think of this angular velocity as being defined by this. It gets crazier if you're in 3D. And then the next step is true in 2D or 3D. It works for anything. The angular acceleration vector, well, we'll just think of all of these as scalars for now. We know they're all z components, but this is equal to the time derivative of omega with respect to time derivative of omega. Okay, so this one is 0.1 t, and this one is just 0.1. And we know that it has a length of 1.5, and we're given the mass. So now I'm just going to start going through the steps of rigid body kinetics. So the first step is, does this thing have a fixed point or not? Does it? Yes. And so the fixed point,
How did we get the 0.1?
that's the, I'm just taking the time derivative of, yeah. So the hinge is our about point. And then our second step is, let's calculate our mass moment of inertia about that hinge. So that is, okay, well, do we need parallel axis theorem for this one? You need parallel axis theorem anytime your about point is not the center of mass. So in this case, we need it. So that means that usually if there's a fixed point, you do need parallel axis theorem, unless the fixed point happens to be at the center of mass. So the formula for the, yep. So for the moment of inertia, we have 1/12 times 15 kilograms times 1.5 squared. That's the one about the center of mass. And then the parallel axis theorem part says add on the mass times the square of the distance from the center of mass to the about point you want. Well, the center of mass of this rod is the midpoint. And so the distance is half of the length of that rod. So this is 0.75 squared. So I get 11.25 kilogram meter squared. What's the third step? Free body diagram. Okay, so the free body diagram. So I'm going to just do it at the same instant that it's drawn, but this free body diagram is meant to kind of represent at any instant. So we have a weight force down of 15 times 9.81. So that's 147.15. And we have a reaction force that we don't know. So that's a fully unknown vector R. And then we're trying to calculate this required external couple, okay, as a function of time. So I'm going to just put that in. I mean, we can imagine that this is, where would you apply this external couple? Probably at the hinge. There'd be a motor in there. Okay, so I'm just going to put this in as some value. I'll call it M. I was about to say reaction moment, but it's not really a reaction. I'll call it ME for external couple. Okay, so those are all the loads acting. Anybody have any questions about that? And now I'm going to go to the table. So my columns are rho, force, moment. My about point is down here. So I'll start out with R. That's the easy one. It's a force at the about point. So the rho vector is 0. The force is Rx, Ry. Cross product is 0. Then I'll do the weight force. And this is the one, this is going to take a little bit of trigonometry. But we already have defined this, this value theta. So the rho vector, somebody tell me the definition of the rho vector. Vector from about point to where the force is applied.
Point of interest or
Yeah, in this case, it's always, the point of interest is always where the force is applied. Okay. So we're going from the red dot to the center of mass. And so that is going to be, the distance is 0.75, and it's going to be 0.75 times the cosine of theta, 0.75 times the sine of theta. Okay. And the weight force is 0, negative 147.15. And so the cross product times, we get negative 110.36 times the cosine of theta. And remember, we still have that formula for theta that we can plug in. Any other loads we have to deal with? Yeah, the couple. So we have to deal with this ME. We don't care about these. And that value is just ME. Okay, what about the sometimes use of step 5? So that's using Newton's second law. Do we need that here? No, because we have a fixed point. So step 6, the moment equation. that says we add up all the moments. So that's 0 minus 110.36 times the cosine of, and I'm going to substitute in what we know theta is now. So 0.05 t squared plus me is equal to the moment of inertia, 11.25, times the angular acceleration. But we also have a formula for angular acceleration, remember? So this says negative 110.36 cosine of the quantity 0.05 t squared plus me is equal to 11.25 times our alpha is 0.1. And so ME is equal to positive 110.36 cosine of the quantity 0.05 t squared plus 1.125. Okay, so if you had some engineering application where you needed this beam to follow this, angular position function, now you know that as time goes by, this is the couple your motor would have to apply. And you would use that to choose the voltage and whatever that you're applying to that motor. Yep.
I was wondering, would you be able to remind me of the definition of a couple?
Yes. A couple is always two equal and opposite forces acting at a distance. That's why we cross out the force part of this table, because they're equal and opposite. So the force ends up being 0. You could also just fill that in as a 0, 0 vector. And remember that the key thing that comes out of a couple that you wouldn't expect, but just we can see it in the math, is that the dependence on the about point disappears. So you can just treat it as this, no matter what your about point is, you treat it the same way. Yes?
So when you're making the three-body diagram, did the problem state that there was a couple there?
Well, you kind of have to read between the lines. Maybe it could have been a little more clear, but we're told what the motion is, and this motion couldn't happen without this external couple. So the fact that, it kind of does, I guess. An external couple is applied, and then it says you're trying to calculate what that external couple is. The guy who words these problems is kind of a deadbeat, but I can't fire him because he has tenure.
Can you fire anyone?
Actually, they don't get me started. They do try. They do frickin' try. No shit. What? They try to fire. No, none of you guys remember. I'm going to pause this. Yeah, right. Okay, so what else we got here in this question? So what's the acceleration vector at the end of the rod at time 5 seconds? Okay, well, now this is just like a watermelon equation thing. So now we can say, so at time 5 seconds, theta is equal to 0.05 times 5 squared. So I'm just plugging it into that function. So that is 5/4, I think. And then omega is 0.1 times 5. So that's 0.5 radians per second. And then alpha is 0.1. That one's constant. And so now the acceleration at the end is alpha cross r plus omega cross quantity omega cross r. So alpha is 0.1. You know, all of these listed up here are just z components. Yeah, they're all signed, so whatever their sign is, that's so this is 0.5. And then r. Okay, well, r is, so this is the vector from, someone give me the definition of the r vector. The vector from,
Center of circular motion.
yes, center of circular motion or spherical motion to the point you care about. So in this case, that is 1.5 times the cosine of theta, 1.5 times the sine of theta, 0. And then we can plug in 1.25. Thank you.
Math.
Okay, so this is 0.106 and 1.496. And then you can plug that in and calculate it. Okay? Any questions about that one? That one has a lot of layers. But it's important to remember that these things here, these are definitions. Those can never be wrong. Okay? Those time derivative relationships. Yep.
Will those always be given in terms of t? Or you can do it?
That's a good question. I think there is one coming up later where you have to use kind of the cross product approach. I think there's only one like that. So the definitions depend on the time derivative, just like with velocity and acceleration and position vectors. But you can use a similar sort of chain rule approach if you have it as a function of like a rotational position variable. Okay. Any questions about 8? We've done something very much like that. And then what were the other ones? 10 and 11? Anybody want to see either 10 or 11? 12 also? Oh, both. Let's see. I'm going to do, I'll do 11. Oh, where'd it go? So first, does this have a fixed point? Yeah, that,
Middle point.
yeah, there's a fixed point at that pin. So A is at that pin. And so now we're going to calculate the mass moment of inertia. And this is going to be a surprisingly tedious step. We have to do two things here. We have to, well, no, we don't really. But so we're going to break this up into two rectangles, figure out the mass moment of inertia of each rectangle about its own center of mass, and then use the parallel axis theorem to figure out the mass moment of inertia of each rectangle about that pin. Okay. And then later on, actually, that's all we need. I was going to say we're going to need the center of mass location also, but we are going to, because that's where the weight force applies. So we're going to have to calculate the location of the center of mass also.
I have a question about the number one. So is A fixed point that the whole structure is fixed to it?
Yeah, so a fixed point is a place on the body that doesn't move in time compared to your inertial coordinate system. So pins and hinges count that way, because if you think of the material point on the body at that point, at that location, that point, is like rotating around the pin, but it's not going anywhere.
So it doesn't, when you say fixed, it doesn't really mean fixed like to a wall.
Right, not like a fixed joint, just a point that doesn't go anywhere. And so you're just looking for hinges, pins.
Yeah.
That's really all, I think. I guess a friction contact would be another example. Okay, so for the moment of inertia, so we'll set this up as one rectangle here, and we want the moment of inertia about a point here, like this is our A. Okay, so, and I'll call this rectangle 1 and this rectangle 2. So the moment, and what do we know about the shape? There's a constant width of 0.05, a constant thickness out of the, oh God, we have to do it with density and stuff. That's all right. Okay, so we have to, so coming out of the page, it has a thickness of 0.1. So rectangle 1 has a volume of 0.6 times 0.05 times 0.1. So that's 0.003. And then the density is 5,000 kilograms per cubic meter. So the mass is the volume times the density. So that's 0.003 times 5,000. And that is, I think that's just 15, right? And then the moment of inertia of 1 about that point A is 1/12 times the mass of that rectangle times the quantity length squared plus width squared. And then we have to use the parallel axis theorem. So that is the mass times the distance from the center of mass of this rectangle to A. Well, notice that the point A is 0.35 from the end. The center of mass of this rectangle is 0.3 from the end because the length is 0.6. So that distance is just 0.05 squared. Well, the distance is 0.05 and we square it. Any questions about that? Yeah. So for rectangle 1, the center of mass is right at the middle. So this distance is 0.3. This distance is given as 0.35. And so the distance from the center of mass of that rectangle to A is just 0.35 minus 0.3. And I get 0.4906 kilogram meters squared. And now I'll go to the second one. The volume of that other rectangle so we have 0.3. It's definitely not drawn to scale. 0.3 plus 0.3 on the other side, plus 0.5 for the middle part. So that is 0.65. Times the width of the rectangle times the thickness. This is 0.3. And this is 0.3. And this is just the width of that other rectangle. So that's 0.05. So this is 0.00325. And so the mass is the volume times the density. So 0.00325 times 5,000. So 16.25. And so the moment of inertia of the second rectangle about A is 1/12 times 16.25 times the quantity 0.65 squared plus 0.05 squared plus the parallel axis theorem part. So there's the mass. And the distance now, we want the distance from the center of mass of this rectangle to A. So that's 0.25 to get to the left side of this rectangle. Um, 0.025 plus the distance from that is 0.25. So 0.25 plus 0.025 is 0.275, I think.
And wait, how did you know it was point? What did you say to get like from that center of mass to the end?
We know the width of this vertical rectangle is 0.05, and we know the center of mass of that vertical rectangle is in the middle. So to get from the center of mass of the rectangle to the left side is half of 0.05. And then the rest of the distance is 0.6 minus 0.35. And so for this one, I get 1.804. Okay, so the total moment of inertia about A is the sum of the two. And so that is 2.295. And, you know, that's a pretty simple shape, but when you start doing this for multiple shapes and having to use parallel axis theorem for each shape and stuff, it gets pretty tedious pretty fast. Okay, so now I'm going to step 2. No, that was step 2. Now I'm going to step 3, free body diagram. And okay, so what loads are acting on this body?
The weight.
The weight. And remember, the weight acts at the center of mass of this whole body. So we're going to have to, that's why we're going to have to calculate that. I'm going to assume it's somewhere over here. And the total amount is going to be the total mass times 9.81. So 15, what's that, 31.25 times 9.81. So this is 306.56. Any other loads acting? There's one more.
Here, sorry, for the weight, what did
I added 15 to 16.25 because that's the total mass. And yeah, there's an unknown force vector at the pin. And I'll call that R. Okay. And so now we're going to have to calculate the center of mass. Okay, so I'm going to put I'm going to do it with a coordinate system. Okay, well, where am I going to put my coordinate system? Have you ever noticed that if you put your coordinate system at the about point for the problem, all your row vectors are just the position vectors where the forces are applied? So if you're ever trying to think about where to put your origin and all things are equal, putting it at the problem's about point is as good as any. So I'm going to put my coordinate system at that pin. Okay. So And I'm going to break this up into, again, rectangle 1 and rectangle 2. And the location x bar, y bar is 1 over the total mass times the mass of rectangle 1 times the centroid of rectangle 1 in this coordinate system, which is just negative 0.050. Everyone, does that make sense to everyone? And then plus 16.25 times the location of the centroid of the vertical rectangle. So that's 0.25 to get to the left end of the vertical rectangle, plus another 0.025. So this is 0.2750. And so so the location of the center of mass of the whole thing is at positive 0.1190. So it's to the right of the pin, a distance of, like looking at the free body diagram, it's to the right of the pin 0.119 from that. So now we can set up the table. We only have 2 forces, just making sure. So first I'll do the reaction force. That's at the about point. So rho vector is 0. The force is Rx, Ry. Cross product is 0. Next, I'll do the weight force. And because we chose the origin at the about point, the rho vector is 0.1190. The force is 0, negative 306.56. So that's negative 36.48. Okay. And that's it. I mean, notice that still 98% of the time we've spent on this problem was just finding the centroid and the moment of inertia. The rest of it is this is a pretty simple problem. Step 5, do we need Newton's second law? Exactly. Step 6, moment equation, rotational Newton's second law. So we have negative 36.48 is equal to 2.295 alpha. And so alpha is negative 15.90 radians per second squared. Does it make sense that the angular acceleration would be clockwise here? If you look at this problem?
Yeah.
Yeah, the weight force is pulling on it to make it rotate around the pin clockwise. And then, so we got the angular acceleration. Then what's the acceleration vector of the point A? That's just another watermelon equation thing. I guess I might as well finish it because we don't have much time left. So this is like the seventh step that we use a lot of the time. So the acceleration of A is equal to alpha cross R plus omega cross quantity omega cross R. We have to be given omega. That's not something we can calculate this way. And it says that omega it has no instantaneous angular velocity, so that's 0. Alpha as a vector is 0, 0, negative 15.90. Omega is 0. And last, R. Someone give me the definition of the R vector.
From the center of the circular motion to the point of interest.
Yes, exactly. Center of the circular motion to the point of interest. So the center of the circular motion is the pin. So this is going to be 0.25 plus another 0.05. So 0.255 and then up 0.255. And then up it's going to be 0.025 plus 0.3, so 0.325. And so use the Pythagorean theorem there and you get, oh, no, I didn't. I need it as a vector. So what did I have before? 0.255, 0.325. And then just plug it in and it'll give you the acceleration. Any questions about that? Okay. Yeah.
What were we gonna go over today?
Just example problems. So yeah, we'll get to those next time, I guess. All right. Thank you.